¿Es en inglés entonces?
Pues no es tan como tú prefieras realmente.
Ok. ¿Prefieren en inglés o en español? Español. Bueno, si llega Nick le cambio. Buenos días, mi nombre es José Núñez. Muchas gracias primeramente por la invitación. Les voy a platicar un poco acerca de lo que es la robótica probabilística y modelos de lo que se llama gaze control. Sonic is here, so I'm going to switch in English. So I'm going to talk about a little bit about what probabilistic robotics is, and then most of the talk I'm going to talk about the gaze control, what it is, and some models of gaze control that I proposed for my PhD thesis. Then I'm going to show you some experiments and results about these models, and some final remarks. Okay, so I think that everybody here will want to have or would like to build some robot like this, right? So I know many people, every time I give some talk about robotics, they expect something like this. The problem is that we are not there yet. In order to have some kind of robot like this, the robot needs to make a lot of decisions and to have a lot of information about the environment. We saw in the previous talk that it's very difficult. There are many things that we need to solve. So the idea is that robot needs to perceive information of their environment using sensors. We know, for example, cameras. And they are expected to perform some action, right? So, and the actions are performed using the motors or the actuators of the robot. The key idea here is that the robot should receive a feedback information from the world or the environment so that the robot knows if the action that is performing is good or bad, okay? So in order to perform some tasks, robots need to make a lot of decisions. In order to make decisions, the robot needs to acquire or to obtain information from the environment. And the more information we have, the better decisions that we can make, right? So I think this is very basic. But what is the problem? The problem is that most of the times, not all information is available. Sometimes we don't have enough sensors, or the sensor is not so good. So the problem is that we don't have enough information and the robot needs to perform some action, right? The other problem with robots is that most of the times it is not possible to wait for new information to arrive. We want robots to behave or to perform actions in real time, so that's another problem, okay? The first problem about information means that robots need to be able to handle uncertainty in a very good way. We as humans, we can navigate or we can, I mean, this is a very messy kitchen. And if we buy a robot to clean our house, we expect to have a robot working in this environment, right? So the first, this environment is very clean, it's a laboratory, so it's very nice. But something like this is like the real thing, right? So it's very important for the robot to be able to accommodate the enormous uncertainty that exists in the physical world and that we are very good at handling this uncertainty. The other problem is about the real time, right? So robots are forced to act even though they don't have enough sufficient information to make decisions with absolute certainty. So what I mean about certainty is that, for example, I need to know where the ball is, exactly where it is, but sometimes I don't know. I mean, the camera or the image processing algorithm or something could be wrong or it's not fast enough. So we need, in any case, we need to make a decision to perform an action, even though I don't have enough certainty or enough information about the world. So that's the key idea of probabilistic robotics. I think many of you know about this, is to represent uncertainty explicitly using probability theory, right? So here the idea is that instead of relying on a single best guess, this means that, for example, I want to know the location of some object, and if I have a not so good algorithm, image processing, for example, using vision. If in some cases we can just apply this algorithm and we will know the location, but probably this location is not correct, but that's the best guess, no? So I'm going to work with that. The idea here is that we use probabilistic algorithms to represent information using probability distributions over a whole space of guesses. So now I know I can get more information and I can summarize or average this information in order to make a better guess. So just to see an example so that everybody understands this, let's see a very basic example about robot grasping, for example. This is not like real, it's just an example. So let's assume that this is what the robot is looking right now. So this is like the camera view of the robot. And the idea is that the robot wants to grasp this ball, okay? So probably the robot the first time doesn't make a very good estimate about where the object is. Why? Because probably the algorithm is wrong, the camera is not very well calibrated. Something goes wrong, right? So the idea with probability, with using probabilities, is that we can obtain more information. Maybe we can run this algorithm several times, and we can get different positions about where the object is. And the end, we can integrate all these results and get a better position. Okay, so that's the idea. As I said, this is not a real example. It's just like because it's very close, so it won't have like it will be like a very bad camera or a very bad algorithm. But we can assume that this could happen. Okay. Okay, so this leads me to gaze control. Gaze control is about the movement of our eyes. So the idea is that we need, as I said before, the robots need to acquire more information, and this information sometimes you need to select which information is the important one. So that's the key idea about this. So gaze control is, gaze, it means it's about the movement of the eyes. And in this case, I'm going to talk about a little bit about, we can see it from two perspectives, the biological perspective and the machine perspective. So from the biological side, we can talk about the movement of the eyes of humans or animals. And from the machine perspective, we have, for example, cameras where they can move, okay? So just to give you an introduction about this topic, I'm going to talk a little bit, about from the biological perspective. So I think because that's what we do, so probably that's a good way to start. And then I'm going to talk about how we managed to model some of these gaze controllers and apply them to a robot, okay? So the first thing that we need to understand is how the eye works. So probably you know that when we see something, the image, the photosensors are in this part of the eye, the retina, okay? And there is a very small part here of the eye. You probably don't see it very well, but this is a very, very small part, which is called the fovea. And that's where the image of what we're seeing is is in high resolution, okay? So this is a graph which represents how the fovea, the distance from the foveal center, how it decrements the acuity of the image that we are seeing. So if you can, as you can see here, this is in this peak, this is where we see like in high resolution, okay? So the rest of the retina obtains just a blurred image of what we are currently seeing. So for example, let's see an example. This image, it's in high resolution, right? You can see all the details, it's very sharp. So the problem is that we actually see like this. There is just a very small part, I don't know if you can see it. There is a very small part here which is in high resolution. That's what we actually, this is how we actually see, okay? So all the periphery is blurred, and just this small part is very in high resolution. Why is this? Because the brain has some parts where it processes this information. If we would like to have, like, if the eye were getting image in high resolution, we will have a very big brain just to process all this information. So evolution helps us to because, okay, so the brain, we think that we see in high resolution, right? So we are able to see everything, and we think that we are seeing everything. We don't think that we see like this. So the problem, the thing is that the brain is doing all this work. Okay, so it's filling the gaps and getting information and trying to, in our heads, we see like this, right? We think that we see like this. Okay, so the key idea here is eye movements. That's the solution that the evolution made about this problem. And there is a special movement. There are several eye movements, but I'm just going to talk about this one, which is called Saccade or Saccade. The goal or the aim of this movement is to shift or to move the fovea to obtain high resolution samples from the environment. Okay, and it has very specific features like this. A Saccade it's a movement, a rapid jump-like movement. The velocity is around 900 degrees per second, so it's very fast. That's why we think that we don't see, we think that we see in high resolution because we're moving our eyes very quickly. And every time we move our eyes, we fixate on something, okay? Another characteristic is that the movements are called ballistic, so the trajectory cannot change. Once the eye starts moving, we stop at some position and then we move to another position. And these movements are voluntary or involuntary. So sometimes we unconsciously are moving our eyes, or probably you have never thought about this until now. So most of the times are unconscious movements, okay? Unconscious, okay, so every time we move our eyes, we are making a decision, so that's the key idea as well. Okay, so this is an example of how we can look at this picture. So this is a fixation point. As I said, when we move the eyes, we fixate on something, we stop the movement, and that's what we call a fixation point. And then we perform a saccade to another fixation point, and then to another. The size of the circle means the time that we look at that position. And that's how we get information, right? So we are sampling the image in this case, or the word, and we are getting this information and filling the gaps, filling the information that we are missing. So the idea is that we perform hundreds or even thousands of saccades every day, and sometimes we don't think about them, okay? And the problem, or the idea here is that each of these movements is a decision that the brain is making, okay? Sometimes unconsciously or sometimes consciously, but it's a decision that we are making. Probably we don't think about them, but that's how we apply this. We get this information from the environment, okay? So one question is, how does the brain decide where to fixate next? Okay, so that's one of the biggest questions. So let's do an example. If I show you this picture, probably you're already seeing several things here. So probably you are looking at this part, or this part, or this object, maybe this one or this one. Yeah. If I don't say anything, if I don't give you a task, then you are just like navigating through the image and just looking around, okay? Probably you see this because it's yellow, so it stands out from the scene, or maybe this one because it's red, in the like brown background. So this is where we don't have any task to perform, okay? So there are several experiments, starting with this experiment from a Russian scientist, where they have this picture. They have some people, and they show this picture to these people and ask different questions about the picture. So, for example, they ask the people, the subjects, for example, what do they think about the ages of the people here in the picture? Okay, so depending on the questions that they were asking, they were looking at different patterns of these gaze movements. So these lines are the movement of how the eyes move in this image, depending on the question. So if you can see that this is like more random, this is very specific. Here they are looking at the faces of the people here of the picture. In some questions they were asking what do they think about the scene? What's the scene about? So probably it's something like, I don't remember, but something probably this one. So the patterns of the eyes move differently depending on the question. So this is very important because this means probably a hypothesis is that task and context determine where to fixate next. Okay, so the decision of where to look, of where we fixate, depends on the task and the context that we are in which we are now. So there are some other experiments. For example, here are some experiments from Mary Hayhoe and Dana Ballard. They use this eye tracker, and they ask people just to perform a task like, for example, making a sandwich. And in this case, you can see all the fixation points and the saccades that the people performed. Again, the circles means the time, the size of the circle means the time that they spent looking at something. And you can see that this pattern is very, very specific, right? So for this task, it's very specific. They just move here on the table where they are working. Here they move outside. Probably they saw something interesting, I don't know. So this is a very nice experiment where you can see that the task that they are performing is very important for the movement of the eyes, okay? So why do we need this kind of movement? So the idea is that we talk about, at the beginning I said that robots or humans as well, we need to reduce uncertainty, okay? We need to get more information. So for example, we can represent the uncertainty about, for example, where the location of this object is using a Gaussian model. So here this Gaussian represents the location uncertainty about this object. This is before looking, for example, and then after we see the scene or we see the object, we can reduce this uncertainty about where the object is. Okay, so this is what we were trying to apply with a robot. So I had two questions that we were interested in answering. The first one is more like what we are expecting here, like just robots and like the engineering side. So the question here is what mechanisms a rational decision maker could employ to select a gaze location optimally or near optimally, given limited information and limited computation time during the performance of a task. So this is important because sometimes we just have, if we don't have a task, then we can just look around and we don't have a very specific pattern. And another question is, of course, how humans select the next gaze location. So this is more like from the biological side, but it's an interesting question. So the idea here is that what we were proposing is something like this. We have different processes for gaze control. So we feed the input of our controller is the information about the task, information about the agent or the robot in this case, the task policy, and this is the input of this fixation selection process. This fixation selection selects obviously the fixation point. Then we get the fixation location that we are going to see next. This is the input of the control that of the process that controls the movement of the eye of the robot, in this case a camera. And then we perform a saccade and a fixation point. Then we get visual analysis and we update the information. And this information is again fed to the, well, it's again an input to the controller. Okay? So this is like the very basic processes that we were working on. And I was just focusing on this process. Okay? So to do this, I used the iCub humanoid robot. This robot is, it was built in Italy. And the idea, well, the goal was to use the real robot. I actually didn't have enough time to do that. So I used first I used the simulator. Right now, that's what I'm trying to do. Right now I have a Now robot, and I'm trying to model these algorithms in the robot, but I haven't finished. And the idea here is that, well, I use the simulator, so sometimes it's not, I mean, it's good because we have a complete control of the situation. The problem is that obviously when we change to the real robot, it's completely different. But, well, okay, so I'm going to show you how this works. Here we had a very simple task. The robot is supposed to get to grasp these objects that are on the table and to put them on these containers. Okay? So actually we have two problems. The first problem is to decide where to look. So the robot needs to choose amongst these different fixation points. Each object is supposed to be a fixation point where the robot is supposed to look. So the first question is to where do I look now? Okay, so where to look. And the other problem that we saw when we use a humanoid robot is that you actually need to allocate gaze to one of the, in this case, to one of the arms. Because sometimes when you move the head of what we saw in the previous talk, the field of view changes and we lost information, or we don't see things that are on the other side. So if we are working with one arm, then probably we want to allocate the gaze to this arm, and then we switch to the other arm, we want to allocate the gaze to the other arm. Okay? So these are two problems. So I'm going to show you a small video about. Okay, because it's a simulation, I can. If you can see, it's not really grasping, it's like a magnet. So, okay. I know that doesn't look good, but it's it's the good thing about using a simulator. So you can see here that this is where the robot is looking. And every time that it performs or it tries to perform an action, for example, in this case, it's trying to grasp this object. So it looks at that object. Then once it has the object, it can move it can shift the gaze to another object so that it can perform different actions at the same time. Okay? So in this case, it's going to drop that object inside the container and then this. So what we are trying to do is to go one step ahead, right? So it's not like, if I need information right now, okay, I am going to look at this object. We were trying to go ahead and try to see first, to go one step ahead of the task, because we knew how the task was. The robot learned the task using reinforcement learning, so the robot knew how the actions and which actions were next. Okay. So I'm going to just to give you a brief example, or like a brief introduction of how this works. I have all the equations and all these kind of things, but I don't think it's enough time to explain everything. So I'm just going to give you like a brief, the conceptual information. Okay. So the idea here is that we have, because I use reinforcement learning, we had a value assigned to all of these objects. So here is the same task. So here we can see a top view of the table. And each object, this bar represents the value of that object, okay? So in this case, because the robot is trying to grasp an object, the value of an object, of reaching an object, is higher than reaching, for example, a container, okay? Also, I had the location uncertainty using particle filters. I was able to represent this uncertainty, the location of the uncertainty about the location of each object using particle filters, and we can measure how uncertain the robot is about something, okay, about the location of some object. If we combine this, then we get a proportion about the location of about the value and the location uncertainty of this object. So as you can see, if you have a very big or very large uncertainty here, the value decreases, right? If we have a very small uncertainty, the value decreases a little bit, not so much. So in this case, this is the best guess that I have about this object, okay? So that's the current value. What we were trying to do is, well, we proposed these three models of gaze control. One of them was based on trying to reduce uncertainty only. Another one was based on rewards and uncertainty. We were trying to increase the reward that we were getting and to decrease uncertainty. And the third model was similar to this one, but we used something that's called the gain. I'm going to explain a little bit more about that. So let's see. Okay. So the idea here, as I said, is that we wanted to go one step ahead of the task that we were doing. So we use one step look ahead gaze control. This is the current time step, the one I showed you before. This is what the robot knows right now. So the idea is that the robot is going to imagine what will happen if I look at some entity or some item for the next time, right? If I see if the robot is doing something, but is thinking ahead of what will happen if he looks at, for example, the container, right? So depending on the task, it's going to measure all this. So the first model is to reduce uncertainty. So the question here that the robot is asking is how much uncertainty is reduced if I look at entity EI, for example, the next time, right? So if we do that, then we try to imagine what will happen if I look at this container. Then this is the current uncertainty, and this is going to be reduced to this. Okay, so this is the residual uncertainty that we had, and this is the previous one, right? So we measure how much uncertainty is reduced, and that's where the robot is going to look at that object in order to reduce uncertainty. So in this case, this is the object that is going to select. Okay. This is in this model. The next model, as I told you, is using reward and uncertainty as well. So in this case, is the question that the robot is asking is how much value am I expected to get after looking at some item? And in this case, I'm going to combine the values and the uncertainty that we had before. So imagine that the robot is trying to imagine what will happen if I look at this object, for example. This is the value that I'm going to get. This is the previous one. And this is the new uncertainty that I'm going to reduce. So in this case, it's going to actually choose to look at this object, which is better because right now, actually the other one, the previous one, it chose to look at the container, and that doesn't really help to solve the task at this moment because it doesn't have anything in their hands. So that means that it needs to grasp an object. So actually this is a good solution or a good answer. And the last one is it combines the problems that I talked about before, where you have to allocate gaze to one of the arms as well. So in this case, the question is which motor system will get more benefit if gaze is allocated to this motor or this arm. So in this case, it's similar to the previous one, but in the previous one, if you remember, we chose this object to look at this object. Now we are going to choose this one because the gain that we get here, the difference between the previous value and the new value is higher here. So I'm going to choose this object instead of this one. Okay. So these are just different models that we were proposing, and we performed some experiments in order to see which one was better. Because we were using a simulator, we were able to do this. In a real robot, it's more difficult, because in the simulator we were able to increase or decrease the sensitivity of the reaching of the object, and the observation noise, for example, as well, and the field of view. So we were reducing the field of view of the robot, or we were increasing the field of view. This means that if we increase the field of view, we see more things. If we decrease it, we see less things, and the robot needs to move the camera on the table. And the observation noise is about probably if we see an object, we don't reduce all the uncertainty, just a little bit, so we can control all these things. And we compare them. We compare these three models with a random model as well, and round robin gaze strategies. So random, of course, is just look wherever you want. Round robin, it was just looking at the different objects one at a time and going in a loop. So here we can see that we increase we decrease this is a very sensitive grasp. So this means that it doesn't have enough room to fail. So this means here 3 centimeters. That means that if the object is 3 centimeters away from the hand, it still grasps the object. So that's not a very good, that's not a very real approximation of a real situation. So the better situation is this one, something like this. So in this case, you can see that this model was better in all these cases where it's actually more important. For observation noise, we have a similar case where this model, where we can allocate gaze to one of the arms, was better than the other ones. In this case, the observation noise was increasing. So that means that even if we look at the object, we still don't get enough information. And in the case of the field of view, we were decreasing the field of view. So we were looking at, the image was very, very small. I mean, not as small, I mean the field of view was smaller. These are the angles that, the width and the height angles of the field of view. And in case of this very small field of view, that means that the robot needs to move the eyes or move the head a lot of times, right, to get information. So still, this model of gaze control was better than the other ones. Okay. At the end, this was just to measure or to check how was the performance of each model of gaze control. We wanted as well, as if you remember, I showed you the biological side of this problem. We had enough time to do another experiment. This is a psychophysical experiment. It's not really about robots, but it's something about how the brain works a little bit. It could be a hypothesis. So they have been a lot of work about how the movement of the eyes, how the eyes are connected to the movement of the hands and all this. So a person called Johansson performed psychophysical experiments with humans, and they have to do this very simple experiment where they grasp this bar and they move the bar to this port, to this target switch, avoiding this obstacle, right? So it's very simple for us. So of course they were in a laboratory, and they had to fix the head of the subjects so that they can measure just the movement of the eye and the hand. I performed something similar with the robot. It's not very accurate, but it's something very similar. And here the idea was just to make sure where the robot was fixating in order to do the same thing. So this is the obstacle, and the robot needs to browse the bar, and then it has to touch this part, the green cube. So it's the same task, and using the same models that I showed you before. So what we obtain is, this is the Johansson's experiment. These are the parts where the subject was looking at for example, at the grasp zone of the bar. The parts where the subject was looking at different parts of the scene. Okay. This is, as you can see, is very similar. These are the results that we obtained with using one of the last model of gaze control that I showed you. This is with the second one. This is with uncertainty, random, and round robin. So if you can see, these three are are completely different, and these two are very similar to this one. I'm not saying that that's how we work, but that's how the brain works, or that my model is very good, and that's how the brain works now. But it's a very nice hypothesis that we can still do a little bit more of research. Okay. Okay. So all this work as well is I did all this work with my supervisor, Jeremy Wyatt, in the University of Birmingham, and right now we have at the in San Luis Potosí we have a team. We have these now robots, and we are trying to do. That's what I am trying to do. These models to apply to these robots. We are working on other projects as well. We are moving also to the part of navigation and mapping, but we are still working on that. Okay. So just final remarks. As I said, robots need to handle uncertainty, and we need a way to obtain more information. Robots need to act in real time. That's a very important issue. And in this case, well, gaze control, I think that could be used to decrease information uncertainty in a very good way. What I'm trying to do is to use these models and apply them to a robot for navigation control. So probably that's another way to apply these models. I don't know. That's what we are working on. So thank you. That's.
We have 5 minutes for questions. 2 or 3 questions.